Okay, first off, I want to apologize. This video was supposed to be one thing, and my internet went out and everything kind of crapped itself. So this is going to pick up from where part one left off. We did that. Oh, here we go. Okay, so if we have, say, we're going to do the same kind of idea here and think about if we take a potassium and a sulfur. So the sulfur has 6 valence electrons, so we do that like so. All right, so initially, the potassium can give the sulfur one of his valence electrons, okay? But it still has one more, still needs one more to get to 8. So what happens is the sulfur finds a second potassium, and that guy gives its electron to the sulfur, and then we can say, okay, then we're going to have a K plus, a K plus, and an S2 minus. Okay. Not too terrible. But because we have 2 potassiums and 1 sulfur, our formula unit for this is going to be K2S. Okay. Yeah, and we're gonna dive into figuring out formulas. Uh, I guess we can do that now. That's fine. We'll go ahead and do it now. I'm a little scattered. All right. So you can always figure this out. Like this is nice in it, but it's a little bit intense. And if you're trying to do things on a rush, it's not going to work very well. But you can uh, figure out what the formula unit of stuff is just from the ions involved. So let's say we had a lithium plus and an N3 minus, right? Because this is 3 minus and this is 1 plus, they have to be totaled to 0. So we're going to need 3 of the pluses to balance out the 3 minus. Okay, does that make sense? I don't know. You can't answer me right now, but there you go. Let's take a stab at another one. Let's say we have aluminum 3 plus and O2 minus. All right, if we're looking at these, uh, now it's not as straightforward. You can do the math way and say, okay, well, this needs to be uh, a multiple of 6, right? Because you have a 3 and a 2. That's one way to do it. Um, and so we would need 2 aluminum and 3 oxygen to get that to work. Another way to do this, I call this the switcheroo. So this 3 ends up being the subscript on the oxygen, and this 2 ends up being the subscript on the aluminum. And so when we do it that way, this will always work for us. This compound should be Al2O3. Okay, so we could have done the same thing with the lithium and the nitrogen, right? 3 ended up over here, and the 1 ended up over there. So it all works. You just have to watch out that you always have the lowest whole number possible for your ratio as you're doing this. So if we do, yeah, let's do this. PB2 plus, O2 minus. We have 2 plus and 2 minus, so we just need one of each. So that's PBO, not PB2O2, which you would get if you did the switcheroo that way. Right, not too terrible, but again, the more you do, the better we get at doing these guys as we go. Let's do one more since I'm running out of room here. A tin 4 plus and a phosphorus 3 minus. That's a 3. Screw it. Okay. If we take those two things, this one we would need a multiple of 12, so we're going to do a switcheroo. The 4 goes on the phosphorus and the 3 goes on the tin, so this is SN3P4. Okay, takes a little bit of practice, but you should be able to get there. All right. Okay, let's talk lattice energy. Remember we said that what's the word I'm looking for? The solid ionic compound force has infinite lattice of stuff. Okay, and that lattice is held together by the ionic bonding that's going on. And we can directly relate this to something called Coulomb's law, because Coulomb's law talks about the energy that's between two charges. So if we look, And I know throwing a formula at us is a little bit terrifying, but if we look, this is our formula for Coulomb's law. Okay. There's no, we're not going to do any math. We're just going to look at it and kind of piece some thoughts together here. Okay. So officially, what we're looking at when we talk about lattice energy is we're looking at the energy to do uh, this process, to take sodium, well, I'm going to use sodium chloride as an example, to take the solid ionic compound and break it into its constituent ions in the gas phase. Okay. As you can imagine, that might take a lot of energy to do that. You can also think of it as this is the energy that's holding the crystal together. So you would need this much energy to break it apart. Okay. So the strength of the amount of lattice energy relates to how tightly those ions are held together. Okay. This depends on two things. One is this guy in the numerator, these Q's. This is the charge on the ions, okay, multiplied together. On the bottom, we have D. This is the distance between them. Okay. This business in the front is just a number. This is a constant. Uh, 4 pi is a number, epsilon naught is a constant. So this is a constant. We're not going to stress about it. I think we even might say our book would call this K, but there's enough Ks in chemistry already. So I'll just put it up there. All right. So essentially what we're saying is the larger the charge, right, the larger the lattice energy, right? And the larger the distance between them, the smaller the lattice energy because the distance is on the denominator, okay? If we compare these three example guys over here, we have lithium and fluorine, we have magnesium and oxygen, and we have scandium and nitrogen. They make a point of showing us that the distance is relatively the same between each one. The big difference here is this is a 1 plus 1 minus, this is a 2 plus 2 minus, and this is a 3 plus 3 minus. And when we do that, there's a huge difference in the lattice energy because the charge is multiplied, right? So this is a numerator of 1, this is a numerator of 4, and this has a numerator of 9. So the increased charge makes the lattice energy higher, okay? Um, if we look at another set of things, then we can see that, right, it's the same idea. Here we're looking at things that all have the same charge, right? This is a 1 and a 1, this is a 1 and a 1, and this is a 1 and a 1, so they're all kind of the same idea. Here the difference is that the iodide is paired with a different cation in each one of these, so the distance between them is different, okay? And what we notice is when lithium is small, our distance is shorter, and the ionization, the lattice energy is higher, right? The same thing here. Sodium gets a little bit bigger, so the lattice energy goes down some. Potassium is bigger, so the lattice energy goes down. Okay. We just want to think about the trends as we're doing this, right? If the charges are bigger, the lattice energy is bigger. If the distance is bigger, the lattice energy is smaller. You can estimate the distance in your head by thinking about the trends that we talked about in terms of ionic size. Okay. Um, Hopefully that makes a little bit of sense. If you're curious for this one, the secret word is penguin. I'll see you around and let me know if you have any issues. Have a good one.